All right, we're looking at L'Hopital's rule. So this is a really great way of being able to calculate limits when the methods that you've already learned haven't worked. So this table here is sort of a discovery table. So we're going to get you to fill in all the information, and hopefully between each column and each row you can see some patterns. So first column here, two functions f and g. So calculate f of 2 divided by f of g. Just leave them as fractions in lowest terms. You'll notice here f of 2, that's going to be 2 squared minus 3 times 2. So 4 minus 6 is negative 2 plus 2 is 0. I guess you can show that substitution here. And then 2 minus 2 is 0. So you really get 0 over 0. So you wouldn't be able to, that's undefined right now, right? So if you were asked to find the limit of f of x over g of x as x approaches 2, we wouldn't know what it is. There is a limit. If you're thinking about it, that's a quadratic over a linear. So basically x minus 2 is a factor of that, so there would be a point discontinuity, which means there could very well be a limit. So let's do our method from calc. So factoring. Okay, dividing out. So then really we're taking the limit as x approaches 2 of x minus 1. So 2 minus 1 equals 1. Okay, so the limit does exist, but by just substituting 2 in, it didn't. Okay, so now let's look at some other properties. Let's take the first derivative of f. So it's going to be 2x minus 3. And then it says find the first derivative when x is 2. So it's going to be 2 times 2 minus 3. 4 times 3 is 1. Now do the same with g. So g prime of x is just a linear, so it's going to be 1 no matter what x is. So that's 1. Now it says find the ratio, so find the f prime of 2 over g prime of 2. So 1 over 1 equals 1. So now if you were asked to find the limit as x approaches 2 of f prime of x over g prime of x, so that's going to be the limit as x approaches 2. F prime of x, remember, was 2x minus 3. G prime of x was 1. So now when you just substitute 2 in, and you get 1. Well, that's kind of interesting. That value of 1 is the same as the limit of f of x over g of x. It was 1. Okay, so those are the same. That's something to look at. Now let's see what happens in the next one. So this is a cubic over a quadratic. So now we're finding f of 2. Oh, sorry, I don't need to show all that. Just substitute in. So that's going to be 2 cubed minus 8 over 2 squared minus 4. 8 minus 8 is 0. 4 minus 4 is 0. Same form as the last one, so we can't just substitute in. So then we use our methods from calc last year. So we want to factor x cubed minus 8. So that's x minus 2 times x squared plus 2x plus 4 over x plus 2 times x minus 2. X plus 2's, divided out the wrong thing there. Just a sec. What do I want to do? Let's see if, okay. Got a little crazy with my crossing out of things. Okay, so this was x minus 2, this was x plus 2. These divide out. So really this is x squared plus 2x plus 4 over x plus 2. And now substitute in the 2, so 2 squared plus 2 times 2 plus 4 over 2 plus 2. 4 plus 4 is 12 over 4, which is 3. Okay. Now, f prime of 2, so let's find f prime of x. So it's going to be 3x squared. So f prime of 2 is going to be 3 times 2 squared, which is 12. Then g prime of x is going to be 2x. G prime of 2 is 2 times 2, which is 4. Now if we take the limit, oh no, sorry, we'll do the ratio. So f prime of 2 is 12, oops, over 4, which is 3. Notice that's the value of the limit of the functions. Now if we take the limit as x approaches 2 of f prime of x, so f prime of x was 3x squared. G prime of x was 2x. If we simplify that, we get 3x over 2. And so then 3 times 2 over 2 equals 3. Okay, so we can find the limit. So that 3 was the same as the limit of the ratio of the two functions. So by taking the derivative of the numerator and the denominator and finding the limit of that, we get the same thing, which ends up being the same as the derivative at that value. Okay. So, third one here, now we're into a radical, so showing that it might work for different functions as well. So let's do, so f of 2 is going to be 2 plus 7 underneath the radical. So that's root of 9 is 3 minus 3 is 0. Oh, I took up a lot of space. We're going to do the whole ratio here, sorry. So that's going to be 2 plus 7 minus 3 over 2 minus 2. So that's going to be 0 over 0. So limit x approaches 2 so x plus 7 minus 3 over x minus 2. Remember, when you have a radical in the numerator, we want to multiply through by the conjugate. And so then that will give us x plus 7 minus 9 over x minus 2 times root x plus 7 plus 3. And so that's going to be x minus 2 over x minus 2 root x plus 7 plus 3. I'm taking up a lot of space here. So that's going to leave you with a 1 up top. Now I'll substitute in. So 1 over 2 plus 7 plus 3. And that's going to be 1/6. Okay? So I did take up a fair bit of space there. I needed to give you more space in this chart. Okay, so f prime of x. So that's going to end up being, so the exponent is really a half. So we bring that down, really, it's going to be 1 over 2, and then the radical in the denominator. Substitute in 2, so that's going to be 1 over 2 root 2 plus 7, that's going to be 1/6. Okay, then g prime of x is just 1, so g prime of 2 is 1. And then this is going to be 1/6 over 1, which is 1/6. Again, that's the same as what we got back in the limit of each function. Now if we go limit x approaches 2 of the derivative, so derivative was 1 over 2 root x plus 7. Derivative of g was 1, so it's really 1 over 2 root x plus 7. And then substitute the 2 in. So we get 1/6. Okay, again, same here as here as here. Okay, so let's summarize. So suppose that the functions f and g are differentiable on an open interval I containing x equals a, and that the derivative of g, so the denominator, is not 0. Then, so basically, if your numerator and denominator is 0, and the denominator at a is not 0, then the limit of f of x over g of x as x approaches a is the limit as x approaches a of f prime of x over g prime of x. Okay, and that is f prime a over g prime a. Okay, so just to summarize again, so if the limit of taking the derivative of f and g, and that ratio equals a value L, then the limit of the original is L, right? So if we can find a limit here, then that's the limit of the original. We may have to use this rule a couple of times, but in any case, by taking the derivative of the numerator and denominator, that's really what's called L'Hopital's rule. So L'Hopital was a mathematician, and he realized these properties. Okay, so let's look at an example here. So you'll notice on mine, it doesn't have what it has for you, part B. Maybe it was cut off here. Yeah. So part B says examples for determining limits with the indeterminate form. So that's what we call indeterminate when you've got 0 over 0. If it's just a number over 0, it's undefined, but we call indeterminate because we don't really know what's happening. So determine each of the following limits. So first of all, you have to see, do we even care, right? So if you can just substitute pi in, then you don't need to do anything else, right? But if we substitute pi into the denominator, we get 0, and the numerator we get 0, right? So here, if we call the numerator f of x, then here f of pi equals 0. Denominator, if we call it g of pi equals 0. Okay, so right now that's 0 over 0. Right now, 0 over 0. So let's use L'Hopital's rule. And oftentimes, when we do that, we just kind of abbreviate to show in our work that that's what you're doing. So L apostrophe H. So limit as x approaches pi. Now we're taking the derivative of the numerator. So that's going to be 2 times x minus pi. Denominator is 0. Derivative of cos is negative sine. Okay. Now if we put pi in now, we get 0 over 0. So we have to do it again, right? So now here, f prime of pi equals 0. G prime of pi equals 0. So we're going to have to do this L'Hopital's rule again. Doesn't matter how many times you do it. So then, again, I'm showing that I'm doing that. Now I shouldn't put equals right next to it. I should just put this up a little bit higher here. Okay, equals, so limit x approaches pi. Now the derivative here is just going to be 2. Sine is cos, so that's going to be negative cos. Now we're good. So now we can substitute in. So that's going to be 2 over negative cos of pi. Cos of pi is negative 1, so that's going to be positive 1. And so that gives you 2. All right, so that means the original limit is equal to 2. We had to use L'Hopital's rule twice. All right, same for the next one. Let's check. So if I put 1 in, so f of 1 and g of 1. So if I put 1 in there, I get 0 in the numerator. In the denominator, 1 cubed minus 1 squared minus 1 plus 1 is 0. Okay. So I'm going to use L'Hopital's rule. I'm going to take the limit, x approaches 1. and the derivative. So that's going to be 2 ln x times 1 over x. And then that's going to be 3x squared minus 2x minus 1. Okay. Now, when I substitute 1 in, there's still a ln x, so that's going to be 0. And then I'm going to get 3 minus 2 minus 1, so I still get 0. So this f prime of 1 is 0, g prime of 1 is 0. So I'm going to have to use L'Hopital's rule again. All right, so I'm actually going to show this keep it as 2 ln x together, okay, and then product rule. So 2 ln, oops, lim, not ln, 2 ln x times the derivative of 1 over x is negative 1 over x squared plus 1 over x times 2 derivative of ln x is 1 over x, so 2 over x. And that's going to be 6x minus 2. All right, so now notice how I have the denominator of x squared. So really, that's a little bit weird. So this I can show as 2 ln x plus 2, sorry, negative 2 ln x plus 2 over x squared times 6x minus 2, which I could factor. Right now, I don't really need to because I'm not going to get a 0 in the numerator or the denominator. So I can just substitute in. So 2 ln 1 plus 2. And that's going to be 2 over 4, which is 1/2. Okay, so that's the limit. Obviously, if you have a calculator and you graph these rational functions, then you would see that it would have a limit. But you don't always, like back in Math 31, you didn't have a calculator, right? Limits where the indeterminate form is infinity over infinity, okay, positive or negative. So again, you can't, you don't know what the limit is, but perhaps it does exist. So we can use L'Hopital's rule in this case as well. Okay, give me a sec here. So we want to check. So if we take a look here, so f of really 0 from the right. So if you think about your ln function, 0 from the right, that's going to equal negative infinity. And your denominator, 0 from the right, it's going to equal positive infinity. Okay, so if you think about the graphs of each of those functions. So let's use L'Hopital's rule. So derivative of ln x is 1 over x. Derivative of cosecant x is negative cosecant x cotan x. Okay. And then you can show that. Let's think about, those are reciprocal trig functions in the denominator. So let's simplify this a little bit. So this is going to be, x is really in the denominator. I'll show the negative out front. Cosecant in the denominator is sine in the numerator. Cotan in the denominator is tan in the numerator. Okay, so looking at that, you might recognize we've got sine x over x. So we could split this up into, how about we do this, sine x over x, okay, and then multiply by limit of negative tan x. Okay, so if you remember, it's on your formula sheet, what the limit of sine x over x as x approaches 0 is, and from the right it would be 1. And limit of, well, negative tan from going towards 0 from the right is 0, okay, and negative is still 0, so that limit would be 0, okay, which is different from negative infinity over infinity. All right, so you do have to show that work to confirm that it's 0. It does exist. The limit is 0. Okay, next one, now we're going to infinity here. So that would be infinity. And then g of infinity is, that's going to be infinity. So here, so we're going to use L'Hopital's rule. And so that's going to be limit x approaches infinity of 1 over e to the x. And now 1 over e to the x as x approaches infinity makes this denominator really big, which makes the whole fraction really small and approaches 0. So that one was pretty fast. Let's move this out here. Sorry, I've got 2 files out. There we go. Okay. Next is if we have 0 times infinity. So somehow it simplifies and you get a multiplication. Okay, so we want to basically change the expression. So you'll notice these examples here. These are all products. There are no fractions. But if we do that substitution, we get, for example, the first one, x is 0 times ln of 0. Well, that's x times infinity. So we want to then change that, if we can, to a ratio of functions, okay, and then use L'Hopital's rule, right? So if we change it to a ratio and we get 0 over 0 or infinity over infinity, we can use L'Hopital's rule and find the limit. All right, so if we look at this, so this is, actually I'm not going to call it f and g because that's what I'm going to do in the next part. But if I substitute in here, I would get 0 times ln of 0, which is 0 times infinity. So that's one of the indeterminate forms. So then I'm not using L'Hopital's rule yet, I'm just changing how I'm expressing this. So ln x, I could leave there, and then x in the numerator is the same as 1 over x in the denominator. Okay, so that's often what you need to do. Go 1 over one of the factors and put it in the denominator. So now if I do f of, call this numerator f, so f as x approaches 0 from the right, that's going to be negative infinity. And then g as x approaches 0 from the right is going to be positive infinity. So I know it's of that indeterminate form. So now I'm going to use L'Hopital's rule. 1 over x, and then this is going to be negative 1 over x squared, which I can simplify. And so that's going to be negative x. Now, 0 from the right, okay, is going to give me 0. Right? So it does exist. Yeah, it's a value of 0, but you've now shown that it does exist. Okay. I just realized up here, ln of 0 is actually negative infinity, but in any case, it's still of that indeterminate form. Okay, next one. So let's check this out. It's a product, pi over 4 for x. So tan of pi over 4 is 1. So 1 minus 1 is 0 times 2 times pi over 4 is pi over 2. Secant, so cos of pi over 2 is 0. So 1 over 0 is undefined. It approaches infinity. There's an asymptote. Okay, so now I want to show this as a ratio. So So I'm going to leave the 1 over tan in the numerator because there's really not a whole lot you can do. But secant is the same as 1 over cos. So why don't I show this as just cos of 2x in the denominator, right? That's pretty easy to do. So now f of pi over 4 is 0. G of pi over 4 is 0. So now I've got that 0 over 0, which I need to use L'Hopital's rule. Okay. So tan, the derivative of tan is secant squared, so that's going to be minus secant, or negative secant squared x. Derivative of cos is negative sine, and it's 2x, so that's going to be negative 2 sine of 2x. Okay. Let's simplify this. So negative over negative is a positive. Secant squared is 1 over cos squared, so this will be 1 over 2 cos squared of x sine of 2x. So now we can substitute it. We've got 1 in the numerator, 2 cos squared of pi over 4 sine of 2 times pi over 4, which is pi over 2. So 2 times root 2 over 2 squared times 1. So that's 2 over 4, which is 1/2, times 2 is 1, so 1 over 1 is 1. Okay, limit does exist. E, so now if we have some limit where the answer is 1 to the infinity, infinity to 0, or 0 to 0, those are also considered indeterminate forms. So we are still going to want to use L'Hopital's rule if we can. Sometimes with these ones though, with the exponentials, we're going to want to maybe use logs to change the form of it. Okay, so take a look at the first one. This is an exponential form. If I substitute 0 in there, I get 1 to infinity, right? So I get 1 to infinity, which is an indeterminate form. So we'll make a substitution. Let's let y equal 1 plus x to the 1 over x. So then if I take the natural log of both sides, 1 over x, ln of 1 over x, okay? And so now I'm going to take, really what I'm doing is taking the limit of y, still as x approaches 0, but we can, I'll leave x approaches 0. You could change what y is, but I'm going to leave it like that, because now that's the same as limit as x approaches 0 of e to the ln y. So remember back to your log rules. If the base of your exponent is the same as the base of the log in the exponent, then that's the same as just y, the argument. Okay? So now if we were to take the limit of, so really in here, e is the base, it's a number. So we really want to take the limit of ln y. And again, just keeping x approaches 0, because now we're going to substitute in ln of y, which we said was 1 plus x, so 1 over x. Okay, remember we can show that using our log laws as that. Oh, not 1 over 2, 1 over x, sorry. Okay. and then we can use L'Hopital's rule, because here, this would be, I'll show it like this, ln, then x approaches 0 of ln of 1 plus x over x. So if we substitute in there, we get 0 over 0. So now we will use L'Hopital's rule. So that's going to be 1 over 1 plus x over 1. Which is 1. Okay, now we're not quite done here. Now we need to think about back up here. So limit as x approaches 0 of ln y equals 1. Then step back from there, that means the limit of y equals the limit of e to the ln y. That's just, I've copied that down from above. Okay, so now we're looking at this. Basically, this goes in here. So this is going to be e to the 1, which is e. Okay, so a few steps. You might want to pause the video, go back, and redo it. Okay, so when you have an indeterminate form with an exponent of infinity or 0, you're going to want to use logarithms. Basically, beauty about logarithms is with the log laws, that exponent that might have a variable in it can then be shown as a factor. Okay, so same with the next one. If we take a look at this. All right, so here, so if we substitute 0 in, we get 0 to the 0, indeterminate form. All right, so then we want to, we're going to let y, you can use any variable, but equal that relation there. Not sure if it's a function or not, actually. So anyway. We'll let y, so then when we take the ln of y, that variable in the exponent then becomes a factor. So that's going to be ln of x. I did that all in one step, right? But that's going to be sine x times ln x. So, therefore, here, limit, so we're really trying to find the limit of y as x approaches 0 from the right. So that's going to be the same as the limit of e to the ln y. That's the same in each one, right? That's the same there and there, just from log laws. All right. We want to find the limit as x approaches 0 from the right of that ln y. Okay. So then what is ln y equal to? From back up here, ln y is equal to sine x ln x. If we put 0 in there, we get 0 times negative infinity. So determinate form, we want to try now to show this as, remember, as a ratio. So leave the ln x. Sine x is the same as cosecant x in the denominator. So now that's going to be negative infinity over positive infinity. Okay, so now use L'Hopital's rule. So it's going to be 1 over x over negative cosecant x cotan x. All right, so the x is now going to be in the denominator. I'll put the negative out front. X in the denominator. Cosecant is the same as sine, 1 over sine. So this is sine of x here, and then tan of x. So that now is, we split this up. You have on your formula sheet, sine of x over x as x approaches 0 is 1. Okay, so that's going to be 1 times negative 0, tan 0 from the right is going to be 0. So negative 1 times 0, which is 0. Okay, so then we have to go back. Limit, as x approaches 0 from the right of y, remember is limit x approaches 0 from the right, e to the ln y. That was our definition statement. Okay, now we have that value to put in. So really, actually, you can just substitute that right now. So that's going to be e to the 0, which is 1. A lot of steps for that. Don't worry, we're not going to give you a whole bunch on the test. Okay, and then last part, examples for determining limits with the indeterminate form where you're adding or subtracting infinity. Okay, again, we want to try to show that as a ratio. So then we can use L'Hopital's rule, all right? So we want to try to show it in those forms. All right, so basically it usually means finding a common denominator. So if I look here, 0 from the right, that's going to be positive infinity minus positive infinity. So we want to try to show this as one fraction. So common denominator is x sine x. Okay, now if I look at this, that's going to be 0 minus 0, 0 times 0. Okay, so we're going to use L'Hopital's rule. It's going to be cos x minus 1 over x times cos x plus sine x. Checking this out, 0 is 1 minus 1 is 0. That's going to be 1 times 0, 0 plus 0. So again, got to do it again. Oops, this one here. Cos is negative sine. X times negative sine x plus cos x plus cos x. Oops, got the 0 there. Okay, so now we get, when we substitute 0 in, we get 0 in the numerator, but we don't in the denominator. We get 2. So it's not an indeterminate form. It actually has a limit of 0. Okay. Then here, same thing. Show it with a common denominator. Going to be x minus 1 minus ln x all over x minus 1 times ln x. So when we do substitute this in, 1 minus 1 is, oh yeah, up here if you wanted to check, 1 divided by 0, okay, so that's going to be infinity, and then minus infinity. So then we're showing it as a ratio. If I substitute 1 in here, I get 0 minus 0. I get 0 here. So now I want to take the derivative of both, so use L'Hopital's rule. So it's going to be 1 minus 1 over x. Then you can use the product rule. And I would get rid of the fractions. So I'm going to multiply top and bottom by x. So it's going to be x minus 1 over x minus 1 plus x ln x. Okay, then if I substitute 1 in there, I still get 0 over 0. So L'Hopital's rule again. So that would be 1 over 1 plus x times 1 over x plus ln x. 1 over 1 plus 1 is 2 plus ln x. And so when I substitute 1 in, I get 1 over 2 plus 0, which is 2. So it's 1/2. All right, we're done. L'Hopital's rule.